A tree is going to be defined as a connected graph in which each edge is a bridge. Now, trees are going to be considered to be barely connected graphs, and because of that, that will imply several things. Between any two vertices in a tree, there is only going to be one path joining them. Also, a tree will have no circuits. And then finally, a tree with n vertices will have n minus 1 edges. So these three ideas right here are going to be things that support this idea of barely connected. But let's look at a few examples so we can wrap our head around what's going on here. So given this initial picture right here, is this picture of the graph of a tree? So for this one, we're going to say no, this is not a tree. First off, this fails to be connected. So that's not going to work out for this being a tree. Now what about in the second picture? Is this picture the picture of a tree? In this case, still no, because this is still not connected. G up here is not connected to the rest of the graph. What about this picture right here? Is this the graph of a tree? In this case, no, this is not going to be a tree. Now while this is a connected graph, this one has circuits. So you can see right here, there's a circuit right here. And you can also consider this guy to be a circuit, this one to be a circuit, and then you can even consider this whole thing right here to be a circuit. In any case, this is not a tree because this has circuits. So far, none of these graphs that we've looked at would be the graph of what I would call a tree. Now let's take a look at this graph right here. Is this going to be the graph of a tree? It will be, yes. So let's see why. This graph is barely connected. If I want to get between any two vertices, let's say for instance I want to get between C and H. There's only going to be one way to get there. C to D, D to E, E to K, K to H. What if I wanted to get from A to L? There's only one way to do that. So for any two vertices, there's only one path joining them. Also notice there's no circuits anywhere in this graph. And in this graph, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In this graph, there are 12 vertices. And I want you to notice that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. Okay, so given n vertices, there's n minus 1 edges. This is going to be the minimum number of edges that we need to connect all of these, and this is also going to be the maximum number of edges that is allowed before anything past this, we're going to start introducing circuits. So this would be the graph of a tree. Now moving forward, some of the things that we want to do is we want to be given a graph, and I want to find a tree using the vertices inside that graph. Okay, so in this picture it says find a tree different than the one already found. So the one already found would be this one over here. So this picture right here takes this graph structure and it omits certain edges but still keeps everything connected. So if you're given a graph and if the tree we find contains all the original vertices of the graph, our tree is said to span the graph. Meaning I can have something that I'm going to build out of these vertices, And for instance, all I need is something that it's a connected graph in which each edge is a bridge. So I could, for instance, grab those two vertices in that edge, and that satisfies the idea of a tree. Okay, this little graph right here is connected, and this edge is a bridge, meaning if I were to remove it, it would disconnect these two vertices. Okay, so that's a tree, but we're looking for a very special type of tree. We're going to look for a tree that has all of the original vertices of this graph. And if I can find a tree that does that, that tree is said to span this graph. Now here's one possible tree over here. Let's try to find another one. So I will need certain edges. This one is not negotiable, and this one's not negotiable because those were bridges to start with. So all of those edges were originally bridges. So all of those will need to be part of my tree. Now the only thing I'm going to look at is to break up these circuits. Now you can see over here, this one grabbed kind of this outer edge. So maybe to come up with something different, maybe I grab this inner edge instead. And then over here, we can see that we grab these ones by grabbing these edges out here, and then this one across the center. So maybe on this one, maybe I'll grab this guy and then come across and then over here. So if I were to grab just those edges, oh, I gotta find someone to come over here to see, huh? How about here? We'll grab him too. If I were to grab these edges, I would contain all of the vertices of my original graph, but I have no circuits, and every one of these edges would be a bridge. If I were to delete any one of them, it would disconnect the graph. Now, we said in a tree, if it had n vertices, it's going to have n minus 1 edges. So let's make sure that I have the right number of edges. Now, I still have 12 vertices here, so I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. So we got the right number of edges for this to still satisfy this idea about being barely connected.